Today's topic, as I mentioned before, is a pretty advanced one, and I'm excited because it's a great opportunity in a database course like this to teach it. And that might seem counterintuitive, but I feel that one of the disservices that's often done when you tackle a large and difficult new concept like reflection is not have a really good use case to explain how and why it's useful. When I was trying to figure out reflection myself, basically everyone's like, oh, well, you can use it to see private, methods and you can work around scope. Well, why would I want to do that? Like the purpose of scope is to keep that stuff protected. Maybe at best they would say, well, you can see into libraries code and understand, how it works better and instantiate their members. Well, if they wanted me to instantiate their classes, they would have made them protected, public, whatever, right? So I I feel that sometimes, these things are tackled in kind of a vacuum, and that does them a serious disservice. For reflection to make sense, you really have to tackle it not in a vacuum. You have to tackle it with a real world problem. And what we're doing is taking our objects from our object relational. I shouldn't say object relational. Sorry, we're taking our object-oriented data model and we're transposing it into a relational data model, which these two things are inherently not the same, as we've talked about before. And in order to do that for any data model that comes our way, and we have no idea what that data model is going to look like from one day to the next. Uh, so just in our one example here for our projects, right? You guys are all working on creating quote unquote the same application, right? The same map cushion application, but your data models are all going to be slightly different from each other. No two, I guarantee you're going to be the same unless you copied each other. So don't do that. And for dflib, the library has to be able to deal with all that, and it has to be able to create your tables based on your classes without having any knowledge ahead of time of how you intend to build those things. And it needs to be able to do it over and over and over again for applications of all shapes, sizes, contexts, anything. And the way it can do that, the way it can create a map cushion database, a SIS, meaning a student information system database, a black card demo database, you name it, any type of application, without having any idea that it's going to be used to do that, is using concepts like reflection. So this is really a great opportunity to dig into a normally pretty deep concept for programming that we have a really good use case for, and that's pretty rare. So it ties everything together perfectly. It goes deep into what we're learning when it comes to linking our applications to our relational data models, understanding the intricacies of the application data model versus the database model, and how it's commonly done, right? And here we go. So, what is reflection? Basically, it's the ability of a process, meaning our applications, to examine, introspect, modify, structure their own behavior, right? Now, their own behavior is a little bit of a loose term here, because remember, in our case, right, we're going to be looking at some examples coming up where we're actually going to be writing reflective code, and I have a GitHub link that you're going to use for that. But in our case, it's actually 4dflib, unless you're doing option 2, that's doing the reflective code, right? Your process is utilizing 4dflib, and it's utilizing reflection to create a relational data model from your data model and manage it. So your own structure replies to basically all of the code that your application is running. It doesn't just convey that it has to be your code off your fingers on your keyboard. I guess it is in the sense that you required the use of using the library, right? So you brought that other code in. But all of the code that has to do with your process, which includes the libraries, is included in that own structure piece, right? Um, just an important thing to think about. It doesn't have to fly off your fingertips. It can just be available through what you're using. It's also important to note that we're going to be dealing specifically with Java reflection here, but reflection is a very common concept across most uh, enterprise level, large scale programming languages, especially on the static side. So we'll talk a little bit more about the differences in a moment, static versus dynamic, and when they, if they're interpreted or if they're compile time. But classic Java, C Sharp, Go, C++, all of these things that are object-oriented languages that are strictly typed and that require are compiled and are required to know type at compile time, and everything really at compile time, need a method like reflection to understand how to look at themselves or any other code that's accessible to them, whether it's a library or something like that. If we look a little bit, if we step back and look at some history here, we can use that to help make how we kind of got to this place a little bit more clear, because at the end of the day, it's all ones and zeros, right? And, if we say there's nuance in code that actually just runs itself, so meaning I have a class named car, I instantiate that class with some data, I run its method, right? That's the normal flow of an object-oriented program. That's no problem. But if I don't have reflection, a object-oriented program, statically typed, compile time program, cannot look at the class car, figure out how many members it has and how many methods it has. It can't, change or view the scope, or if it has annotations, anything like that. For you to know that, you have to look at, on a regular language, not using reflection, you have to either look at the documentation or have access to the source and look at it yourself as a human, right? And then you say, oh, okay, there's a name here, right? And there's, an ID, and there's all these different fields, and there's these methods, and to call the method, I pass it this information. But if you don't have reflection in this world, you can't dynamically look for that. You can't just say, okay, this is a class of type car, and a class, I can get the members of the class. Let's say there's like 6 different data members, and I can iterate through them in a loop, and I can find all the methods, and I can iterate through those, and I can find all of the superclass methods and the superclass members and the annotations and all of this other stuff. And I'm using code to explore my code. That's what reflection is. And historically, this wouldn't have mattered, because if you go back to like assembly days, stored program concept is very clear, right? Every slot you have in memory can be data, it can be instruction, it doesn't matter. There is nothing special about the locations in memory where your program is stored that a computer knows that only programs get stored there. They are just addresses in memory. So if you have a program counter or an instruction pointer, all you're doing there is you're pointing your CPU to the current place in memory where it's supposed to look next for the next thing to do. And it doesn't actually know if that's an instruction or data. Hopefully it's an instruction if you're acting on it, right? But maybe you're getting it from memory to add it or subtract it or whatever. So all we know is that, we have bits in memory and we're processing them. And if you think about how that works at an assembly level, those of you who might have had me for Org and Arc might be having flashbacks right now. We can look at anything we want, right? If we want to do some introspection on our data, sure, no problem. We just figure out where that information is stored in memory. We pull it out and put it in some registers. If we want to know the name of the data type, sure, that's in there too, right? It's all stored. So that's easy. But when we went to high level languages, a lot of that ability was inherently lost. We weren't able to self-examine our code at runtime. We actually examined it as humans by reading it, right? Like I said before, and knowing what this class had and knowing how to instantiate it. But we weren't able to use code to actually read the code. And this was not important when you were, just working in your own code. But once you say and want something dynamic to happen, where say your code is going to accept a class from another bit of code that hasn't been written yet, or at least you don't know what it's going to be, like our classes like car and driver, you can't do that, right? You lose that ability in our high level languages. And that means that we're constrained on what we can actually do. So in order to get back to that place, in order to be able to give the processor the guarantees it needed at compile time to still build the code, and say, yeah, you're going to work with some classes that a person's going to give you, and you're going to be able to look at those classes, but you don't have them yet, and that's okay. We had to develop this concept of reflection. So it satisfies the compiler at compile time that the types that are required are all going to be there. And we actually talked about that a little bit last week. Let's kind of like rewind that bit to explore it, because it's something that's important. Remember that all of the data types that we're going to store using 40flib have a requirement that they extend common services, right? And we said the reason for that was that common services had, I believe it's the 7 attributes that are always stored in every 40flib table, like the ID, the RID, the start date, the end date, the user ID, that kind of stuff. Those are the things, the current flag, the deleted flag, all that good stuff. Those are the things that allow 40flib to keep all the records, audit things by time, and all that good stuff. But we said, because we have that, and all of the classes will extend common state, and we saw that with the generics of when we pass a class, right? It said S extends common state, meaning the compiler says whatever class type you pass this method, it has to extend common state. That's the contract. Because it does, I know that I can use the ID method or the RID or the start date or the end date. So I can search these records by date, and I can search them by ID without knowing ahead of time what class type it is, because all class types you're going to pass me extend common state and therefore have these particular members that I'm working with, right? So those are the kinds of guarantees I'm talking about. So generics, that ability to just pass some class or some type or something like that, and the ability to use reflection come together to allow us in a statically typed compiled language to still be dynamic and still do things at runtime within the contract of what we tell the compiler. We tell the compiler that we will give it a class of a certain subtype, or that it extends a certain type, or whatever it is, right? Or that it has an interface. Those are the rules that we have to play by. So once that was all established, then we could get back to that dynamic world that we wanted to be in, where we could use a library like 40flib to examine any code, any data model, and create a database from it, manage it, all those good things. All of that is possible because we put into place those things. Reflection allows us to inspect classes, interfaces, fields, and methods at runtime without knowing the names of those things. And this might sound a little hard to digest, and I hope it doesn't, but what I'm going to do is, after we kind of go through the terms here, I'm going to dig in with actual code. I have that GitHub repository I mentioned before, and we're about to dig into it shortly. And I'm going to show you these things, and then you can practice them yourself. So hopefully that will make it more real. Even though 40FLib is responsible for these things, for you to understand them, we're going to play with them ourselves and see how it works, because that, I think, is the most important way to actually convey a difficult topic like this one. Okay, so a couple of just other footnotes. We can use this to look at classes and everything about them. We can use it to call methods. We'll see that. So there's actually an invoke that allows us to call a method that we have associated with a class. It's important to note in general that this might be a little bit slower than some other types of statically typed code. Because it is not known at runtime all of the information that we need to satisfy the just-in-time compiler, the JIT, it can't optimize all of that code for runtime. So the just-in-time compiler is a method that the JVM uses to basically take, this is why they tell you if you use final, for things that won't change, it's going to make your program faster because it's going to store it in a different place in memory, and it's going to be more accessible, and it doesn't need to go back and get it, that kind of thing. So that's all these optimizations that can be made because things aren't going to change. Statically typed languages are great at this because they are generally, everything you need to know is generally known at compile time, except for like your instance variables and things like that. When you use reflection, you are taking away more of the things that the just-in-time compiler can optimize in that nature. So this is not a deal breaker. It's not to say like this thing's going to run slow as molasses. It's not. It's just a trade-off, and it's an important one to know because if you are creating code that's supposed to be, run at huge scale and have like millions of hits a second or something, you might want to think about this, right? That's important. But by and large, I don't think you're going to sense or see the differences when it comes to the optimizations here. It's not something that's going to be like readily apparent in how fast your application runs unless you're at extreme scale or extreme amounts of dynamic use. Also, if you've used JavaScript, I wanted to point out that the prototype in JavaScript is very similar to what we're doing here. JavaScript is not a fully object-oriented programming language. For example, it doesn't support inheritance, which is one of the main principles of object-oriented programming. You can't have a superclass in JavaScript. What JavaScript is a prototype object-oriented programming language, which means that essentially what it does is it gives you the ability to look at a type, and because it's dynamically typed JavaScript, basically it creates types on the fly, and when it does, it's creating a prototype that defines that type. So when you create something, it's like, do I have a prototype for this type right now? And if it doesn't, it creates one. So for our car and driver and those classes that you saw in the black car example that we're also going to use again today, in JavaScript, there would be a prototype of those. So you could say car.prototype, and then you could actually access its members and methods. You can actually change them. You can actually add new methods and stuff after the fact, and it even affects the current instances of it. Reflection and prototype are not 100% the same, but I just want to point out that there are similarities. It's a way in JavaScript that you can inspect your own types, your own classes, and learn about them and change them. And reflection in Java is pretty much the same idea. It is a little bit different, and it is in a statically typed environment, so you don't have as much power as you do with JavaScript prototype. But if you've used it, this is a similar concept, so that might help give you something to relate to. All right. Last thing I just want to point out here, this is a little bit of code. I'm not going to spend a lot of time here because we're about to do a deep dive on actual code. But I wanted to take a moment just to show this. This is actually off of Wikipedia. The Wikipedia article on reflection is a good kind of place to start thinking about this. I'm going to link it with some other resources that are intended for further reading past this lecture. But basically what's happening here, it's important to note that we have to use try-catch situations anytime that we're dealing with reflection. Right now I have catch exception here, and you'll see as I go through some of the demos that I will use that occasionally. But I've also listed some of the specific types of exceptions that you could expect to find in code such as we have in this try block. Always try to be specific about your catches when you can. Obviously having the catch exception is better than nothing. But what I like to do is if you're not certain about which ones you're going to find, do the catch exception and then look to see what comes out in the output. But most IDEs will help you with this now, and you'll see that as I go through. If you automatically put catch exception around everything, then they won't, because they know that you've already kind of given it a blanket catch, and they'll ignore it. But that aside, what we're doing here in the first line inside the try is we're actually creating an object. So you know how to do this normally. So what we're doing here is we're creating an object of type foo. So there is a foo with a capital F that we're creating. And instead of just saying, foo equals new foo, we're saying object foo, because remember, everything in Java is a child of the object class, right? It inherits from object. So we're just saying object foo, meaning that the thing you're going to get is going to be something that can be a subclass of object. Everything can be, right? And then what we're going to give it, this first one isn't the more common way to do this, but we're using capital class. So this is a reference to a static class called class. And then the method is forName, and this is a static method, and we're passing in the complete package and name of foo, so complete class path and foo. And then at that point, so up until here, right, before this period, from here to here, we're referencing, foo here as a class. And then this dot new instance is actually going to create an instance of that class, kind of like calling the constructor. And it's then going to take that instance and put it here in object foo. Alternatively, and this is the one that you'll see more often done with reflection, you can also have object foo, same as before, equals foo, so we're referencing the actual class foo this time, dot class. Now this is where all classes, you don't have to add this. This is something that you get for free in the Java library. All classes have a dot class, and that is a reference to the actual class of the object, right? Or the class in this case, because it's not instantiated yet. So I'm saying foo.class, so I'm referencing it as a class, dot new instance. And that's going to, this is the same as saying new foo, right? That's essentially what we're doing here. It's just doing it through reflection instead of the standard instantiation process. Now down here, we're actually getting a method associated with the class. So notice here that we have our object foo. This is an instance. We're getting its class again. So you gotta bring your brain, kind of remember when you're in an instance, when you're in a class. So we have the instance, but now we're getting its class. So again, now we're referencing the class at this point, not the instance, and we're getting a declared method of that class called hello. So you can imagine that we're saying, look through the class and see if there's a method in there called hello. And you can also pass parameters here. Don't worry about this one here. I'm just going to ignore that one there. We're going to do a different version of this that's a little bit easier to digest. But all you're doing here is getting the declared method. In this case, we're looking to see, is there a method called hello? If there is, we're going to end up with a reference to that method here as m. Now remember, this is a reference to the actual method of the class, not the method of the instance, and there's a difference there. If for some reason there was not a hello, you would have gotten this no such method exception. Just like up here, you would have gotten a no such class if these had failed. And now what we're going to do down here is actually call that method. So remember, this M is a reference to an actual method in a class. It's the definition of the method, kind of like in JavaScript when you were going into the prototype and looking at the definition of a method, right? And I'm saying m.invoke, so call this method, and what I'm passing into it is the actual instance I wanted to call it for. So if there was instance related data in this object's method, it would use that data when you invoke the method. So it's like what this is doing is it's basically like calling the method hello in foo. Now this might be like a little bit brain warping right now, and you might be wondering why I would do this, kind of like picking your eyeball out with a spoon, in comparison to just doing it the normal way. But I will show that a little bit more, and when we dig into the code, I think you'll see some more of its value, especially when we put in the context of what we're actually doing with 4dflib. So with that, this was it for the kind of definition of what reflection is in the initial discussion. The next video will have an in-depth kind of code exploration where we're going to use the GitHub repository that I have linked.